A sloth, a donkey, and a curious human. Send a prompt and see what they're doing. One hits record with a question on his mind. Two brothers pick it up, see what they find. Corn takes his time, Herman's got the facts. Back and forth, they never hold back. My weird prompts, come on in, that's where we begin. My weird prompts, glad you're here.
This episode was generated using artificial intelligence. Please verify facts.
You know, Corn, this whole show runs on GPU compute, and we wouldn't be here without Modal.
Seriously. And that's what powers all our text-to-speech. Everything you're hearing right now.
They're an AI infrastructure platform. Developers use them to run GPU workloads in the cloud with zero infrastructure headaches.
If you're building anything with AI, check them out. Modal.com. You know, Herman, I was looking at some old tech blogs from the early 2010s the other day, and it struck me how much we act like we discovered fire every time a new rag paper drops. We talk about two-stage retrieval like it's this brand new, cutting-edge architecture that just fell out of the sky last Tuesday.
It's the classic amnesia of the tech industry, Corn. We're standing on the shoulders of giants, but we're mostly just complaining that the giants didn't have a high-latency API we could plug into. We treat the past like it was just caveman search, but those cavemen were managing millions of queries per second on hardware that would struggle to run a modern refrigerator.
And speaking of giants, today's prompt from Daniel is pulling us back into the history books to look at Google. He wants us to trace the lineage of re-ranking, how Google used it to save search results from the dark ages of keyword stuffing, and how those exact same principles are basically the only thing keeping modern retrieval, augmented generation, from turning into a hallucination factory.
It's a fantastic angle because it grounds the AI magic in actual engineering history. And honestly, it's a perfect day to dive into this because today's episode is actually powered by Google Gemini 3 Flash. It's a bit meta, isn't it? Using a Google model to discuss how Google basically invented the playbook for the systems that now run on, well, Google models.
It's the circle of life, Herman, or at least the circle of compute. But before we get into the weeds of cross-encoders and vector debt, let's set the stage. If you go back to, say, 2010, Google search was good, but it was still very literal. If you search for, "Why is the sky blue?" it was looking for those exact words. How did they move past that without melting every server in Mountain View?
That is the trillion-dollar question. See, the core problem Google faced, and the problem every AI engineer faces today, is the scale versus sophistication trade-off. You have billions of documents. You cannot, under any circumstances, run a complex neural network over all of them for every single query. You'd need the power of a medium-sized star to handle the peak Monday morning search volume. Think about the math. If you have a billion pages and you spend just 1 millisecond of CPU time evaluating each one, a single search would take over 11 days to complete.
Right, because even back then, latency was the killer. If a search took 3 seconds, people just went to Bing. Wait, no they didn't, but they thought about it.
Precisely. So Google perfected what we call two-stage retrieval. Stage 1 is the wide net. You use something computationally cheap like BM25 or basic keyword indexing to grab the top 1,000 potentially relevant pages. It's fast, it's dumb, but it reduces the search space from billions to thousands in milliseconds. It's basically a massive filter that says, I don't know which of these is the best, but I know the answer isn't in those other 990 million pages.
But how does it know that? If it's dumb, isn't there a risk it throws the baby out with the bathwater?
That's the risk of recall. In stage 1, you optimize for recall. You want to make sure the right answer is somewheres in that top 1,000. You don't care if it's at position 1 or position 900, you just need it on the guess list.
And stage 2 is the re-ranker. That's where the actual brains live.
That's it. In stage 2, you take those top 1,000 results and run them through a much more expensive, much smarter model. Because you're only looking at 1,000 documents instead of a billion, you can afford to spend more thought per document. This is where Google started introducing lightweight neural models long before anyone was talking about large language models.
It's funny because we think of AI in search as a post-2022 phenomenon, but Google was doing this with the knowledge graph back in 2012. They were using models to understand that Taj Mahal, the monument, is different from Taj Mahal, the blues musician. How did the re-ranker actually distinguish those two if they both had the same keywords?
It looked at the context of the user and the surrounding words. If your previous search was greatest guitarist of all time, the re-ranker would see Taj Mahal in the retrieved list and give the musician a massive boost in the scores, while the marble mausoleum in India would get pushed down. It was using a point-wise scoring system, looking at the query and the document as a pair and asking, on a scale of 0 to 1, how much does this specific person want this specific page right now?
I love that. A two-layer network. Nowadays, if your model doesn't have 100 billion parameters, people won't even use it to summarize a grocery list. But back then, it was about efficiency. They were scoring document query pairs using learned weights. Basically, the model wasn't just looking for the word blue and the word sky. It was looking at the relationship between the query and the document content in a way that basic indexing couldn't touch.
And the mechanism is what's really fascinating. These early re-rankers were essentially point-wise rankers. They would take a query and one document, feed them into the network, and spit out a relevance score. You repeat that for the top 100 results, sort them by the new score, and suddenly, the most helpful page jumps from position 50 to position 1.
It's like a bouncer at a club. The retrieval stage is the line outside. The bouncer, the re-ranker, doesn't look at everyone in the city. He just looks at the people in the front of the line and decides who actually fits the vibe of the party.
That's actually a rare, decent analogy from you, Korn. But here's the technical kicker. Those early models were the precursors to what we now call cross-encoders. In modern RAG, we have this distinction between bi-encoders and cross-encoders, and understanding this is the key to Daniel's prompt.
Okay, let's break that down for the folks at home, because every time I hear bi-encoder, I just think of a model that can't make up its mind.
Very funny. A bi-encoder is what your typical vector database uses. It turns the query into a vector, turns the document into a vector, and then does a quick mathematical comparison, cosine similarity to see if they're close in space. It's incredibly fast because you can pre-calculate all the document vectors. But because the model never sees the query and the document at the same time, it misses the nuance. It's like trying to judge if two people are a good romantic match by looking at their resumes separately without ever seeing them in the same room. You see they both like hiking, but you don't see that one likes hiking in the Alps and the other likes hiking to the fridge.
And the cross-encoder is the in-the-same-room moment.
A cross-encoder takes the query and the document, mashes them together into a single input, and feeds them through the transformer. The model can use its full attention mechanism to see exactly how this specific sentence in the document answers that specific part of the query. It can see that when you asked for lightweight jackets, this document about photon weight shells is a perfect match, even if the words are different. It's orders of magnitude more accurate, but it's much slower because you have to run it in real time for every query document pair.
So we've basically circled back to Google's 2012 strategy. We use the fast, dumb vector search to get the top 50 chunks, and then we bring in the smart cross-encoder to tell us which 5 chunks are actually worth showing to the LLM. But wait, if the cross-encoder is so much better, why don't we just use it for everything? Why even have the vector database?
Because of the n-squared problem, Korn. If you have 10 million documents and you want to use a cross-encoder to find the best one, you have to run 10 million inference passes. Even with the fastest GPUs on Earth, that's going to take forever. The bi-encoder, the vector search, is the pre-filter. It's the stage 1 that makes stage 2 possible.
We have. And the reason this is seeing a massive resurgence in 2024 is because of the lost in the middle problem. There was a very influential paper by Liu and others that proved LLMs are actually pretty bad at finding information if it's buried in the middle of a long context window. If you give an LLM 20 documents and the answer is in document number 10, the LLM often misses it. It pays more attention to the beginning and the end.
It's a fascinating quirk of transformer architecture. They have this U-shaped performance curve. They are great at the start of the prompt, great at the end, and remarkably mediocre in the middle. It's almost like the model gets tired halfway through reading your context and starts skimming.
It's got the attention span of, well, me. It remembers the start of the conversation and the very last thing you said, but everything in the middle is just white noise.
Precisely. So re-ranking isn't just about relevance anymore, it's about context window optimization. By using a re-ranker, you ensure that the most statistically relevant information is at the very top of the prompt. You're literally spoon-feeding the LLM so it doesn't have to work as hard to find the truth. You're moving the needle from here is a pile of data to here is the specific answer you need located right where you are most likely to see it.
It strikes me that this also solves the hallucination problem to some degree. If the retriever brings back something that looks semantically similar, like a document about Apple stock prices when the user asked about apple pie recipes, the re-ranker can see that mismatch instantly. The vector search just saw the word apple and got excited. The re-ranker sees the context and says, "No, this is about finance, not baking. Move it to the bottom."
That's a huge part of it. Vector search is notorious for false positives based on keyword overlap or similar themes. A re-ranker acts as a high-fidelity filter, and what's interesting is how the industry is productizing this now. You look at companies like Cohere or NVIDIA, they're releasing specialized re-rank models. These aren't general-purpose LLMs, they are purpose-built models designed to do one thing, score the relationship between a query and a passage.
I saw a case study recently. I think it was from a startup early last year, where they were struggling with RAG latency. They were trying to feed 30 chunks of data into a massive model to be safe. They switched to a two-stage process. They used a tiny 1 billion parameter re-ranker to filter those 30 chunks down to the top 5. Their latency dropped by 40% because the final generation model had so much less text to process, but the accuracy actually went up.
It's the less is more principle of data engineering. And it's funny because if you told a Google engineer in 2015 that this was a breakthrough, they'd just stare at you. They've been doing this with RankBrain and BERT for years. When Google integrated BERT into search in 2019, that was a re-ranking play. They weren't re-indexing the whole web with BERT, they were using BERT to understand the top results and reorder them. They realized that BERT was too heavy to use on the initial retrieval, but perfect for that final sanity check.
So, why did it take the RAG community so long to catch on? Was it just the shiny object syndrome of the vector database?
Partly. Vector databases were the new thing, and they promised semantic search as a cure-all. People thought that if the embeddings were good enough, you wouldn't need a second stage. But as we've pushed RAG into more complex enterprise domains, legal, medical, technical documentation, we've realized that semantic similarity is a very blunt instrument. You need that second stage reasoning. If you're a lawyer looking for a specific case precedent, similar isn't good enough. You need exactly relevant to this specific legal theory.
It's also about domain specificity, isn't it? Google's re-rankers are trained on the entire web. But if I'm building a RAG system for a company that makes specialized hydraulic pumps, a general-purpose embedding model might not know the difference between two very similar-looking part numbers.
That's where fine-tuning re-rankers becomes the secret sauce. It is much, much easier and cheaper to fine-tune a small re-ranker on your specific data than it is to fine-tune a massive generation model. You can teach a re-ranker exactly what relevance looks like in your specific niche. You provide it with pairs of query, how do I fix the seal on a P500? And document maintenance guide for P500 seals, and you tell the model this is a 1. Then you give it the guide for the P600 and tell it this is a 0.2.
Let's talk about the LLM as a judge trend, because that feels like the modern evolution of this. I've seen people using models like Mistral, or even smaller specialized models, to literally read the search results and give them a score from 1 to 10. Is that just re-ranking with a more expensive hat on?
It is, but with a twist. The judge model can provide a rationale. It doesn't just give a score, it can say, this document is relevant because it mentions the specific torque specifications the user asked for. That's incredibly useful for debugging your RAG pipeline. You can actually see why the system chose document A over document B, but for production at scale, you usually want to distill that judge knowledge back into a faster, more traditional re-ranker.
It's like having a master chef taste the soup and tell the line cook what's wrong. You don't want the master chef standing there 24/7. You want the line cook to learn the lesson so he can do it faster next time.
And this brings up a really interesting point about the vector debt we've talked about before. If you rely solely on your embeddings, you're stuck with whatever understanding was baked into that model when you indexed your data. If you add a re-ranking layer, you can swap in a better re-ranker every week without ever having to re-index your billions of vector embeddings. It gives you this modularity that's essential for staying current.
That's a massive practical takeaway. If you're building a RAG system today and you aren't using a re-ranker, you're basically leaving performance on the table. It's the easiest way to improve your system without a massive architectural overhaul. But how do you actually implement it? Is it just a line of code?
In many modern frameworks like LaILMA Index or LangChain, it literally is just adding a node post processor. You initialize the re-ranker model, tell it how many documents you want it to return, say the top 5, and it sits between your retriever and your synthesizer. It's a middleware for meaning.
I think we should emphasize to the listeners, start simple. You don't need to build your own neural network from scratch like Google did in 2013. You can use open source re-rankers like the BGE re-ranker from the Beijing Academy of Artificial Intelligence. It's a top-tier model that you can run locally, and it will likely outperform a basic vector search by a wide margin.
And if you're feeling fancy, you can even use a cross-lingual re-ranker. Imagine your documents are in German, but your query is in English. A bi-encoder might struggle to bridge that gap perfectly, but a cross-encoder can look at both simultaneously and realize they are talking about the exact same technical concept.
What's the catch, though? There's always a catch. If I add a re-ranker, my time to first token is going to go up, right? I'm adding another step in the middle of my pipeline.
Yes, there is a latency cost. This is the same trade-off Google has managed for 15 years. If you re-rank 100 documents, you might add 50 to 100 milliseconds to your pipeline. But here's the counter-argument. By only sending the top 5 documents to your LLM instead of 20, you save hundreds of milliseconds on the generation side. In many cases, adding a re-ranker actually makes the total pipeline faster while also making it smarter.
Right, because the LLM doesn't have to chew through all that extra fluff. It's like cleaning your windshield before a road trip. It takes a minute, but it makes the whole drive much easier. You're not wasting attention on garbage.
And if you're really worried about latency, you can do what the big players do, Colbert or late interaction models. These are a middle ground between bi-encoders and cross-encoders. They store more information about the document, essentially a vector for every single token, but still allow for very fast re-ranking. It's a bit more complex to implement, but it's how you get that Google speed feel with modern transformer power.
It's fascinating how much of this comes back to basic information retrieval theory. We spent a decade trying to disrupt search with AI, and we ended up rediscovering that the search guys already solved most of these problems. They just didn't have the marketing budget for large language models.
Well, they had the budget, they just called it search quality. And that leads us to a big second-order effect, the death of the long tail. One of the things Google's re-ranking did was vastly improve results for long-tail queries, those weird, specific 5-word questions that don't have a lot of direct matches.
Oh, I know those. How to fix a leaky faucet while my cat is screaming.
Right. In the old days, you'd just get pages about faucets and pages about cats. Neural re-ranking allowed Google to understand the intents of the whole phrase. In RAG, this is even more critical. Users don't ask simple questions. They ask complex, multi-part questions that require synthesizing information from 3 different manuals. A vector search will almost always fail to find the perfect chunk for that. But a re-ranker can look at the chunks that are close and find the one that actually addresses the nuance.
It's about the connective tissue of the information. Vector search is good at finding the bones, but the re-ranker finds the ligaments that actually hold the answer together. It understands that screaming cat in that query isn't the primary subject. It's a constraint or a context for the faucet repair.
And let's look at the future side of Daniel's prompt. Where is this going? We're already seeing native multimodal re-ranking. Think about searching a database of videos or images. You don't just want a description that matches. You want a model that can re-rank the frames of a video based on the actual visual relevance to your query. If you search for man jumping over a fence, you want the re-ranker to find the exact 3 seconds where the jump happens, not just any clip with a fence in it.
That sounds like a nightmare for compute.
It is, which is why the 2-stage approach is even more important there. You use cheap visual embeddings to find the right video and then a sophisticated multimodal model to re-rank the specific timestamps. We're seeing the same pattern repeat everywhere. It's the only way to handle the sheer volume of data we're producing.
I wonder if we'll eventually see re-ranking just disappear into the models themselves. Like, will the next generation of LLMs be so efficient at long context that we don't need to filter the data? We just dump 1,000,000 tokens in and let it sort it out?
Some people think so, but I'm skeptical. Even if the context window is infinite, the cost per token is never zero, and more importantly, the noise to signal ratio is a real thing. Even the smartest human in the world will do a better job if you give them the 3 most relevant books instead of a whole library and tell them to figure it out. Re-ranking is essentially attention management for AI. It's about high-density information.
Attention management. That sounds like a self-help book for robots. But it makes sense. We're protecting the model's limited cognitive resources, or at least its expensive ones. If you're paying by the token, you really don't want to pay for the model to read the table of contents and the About the Author page.
And for the developers listening, there's a very tactical lesson here. Don't over-engineer your embeddings. I see people spending months trying to find the perfect embedding model or the perfect chunking strategy. Often, you're better off picking a good enough embedding model and spending that time fine-tuning a re-ranker. It's a much more high-leverage way to improve your system. It's the difference between trying to build a better net and hiring a better fisherman to sort through what the net caught.
It's the 80-20 rule of RAG. 20% of the effort adding a re-ranker gets you 80% of the accuracy gain.
And it's a great example of how old tech becomes new, again when the context changes. Google wasn't trying to build AGI in 2012, they were just trying to make sure you found the right pair of shoes. But the math they used to do that is now the foundation of how we build reliable AI agents. They were solving for truth and utility in a sea of spam, which is exactly what we're doing with LLMs today.
It makes me feel a bit better about the world, honestly. It's not just a chaotic explosion of random new stuff. There's a thread of continuity. We're just taking the bouncer from the 2012 Search Club and giving him a much faster brain and a better suit.
And a much higher hourly rate. But the job description is the same. Keep the junk out and let the good stuff in.
So, if we're looking at practical takeaways for someone building a RAG pipeline right now, step 1, check your retrieval. If you're just using cosine similarity on a vector database, you're in the pre-2012 era of search. You're basically building a very fancy keyword search that can handle synonyms.
Step 2, implement a re-ranking stage. Even a simple off-the-shelf cross-encoder will probably give you a massive boost in precision. And step 3, measure the lost-in-the-middle effect in your own data. If your LLM is missing answers that are present in your retrieve chunks, your re-ranker is failing you, or you're not using one. You can test this by manually moving the correct chunk to the top of the prompt and seeing if the answer suddenly appears.
I'd add a step 4. Look at your latency budget. If adding a re-ranker adds too much time, look at smaller distilled models or late interaction architectures like Colbert. You don't have to sacrifice speed for quality. You just have to be smarter about where you spend your compute. And maybe consider if you really need to re-rank 100 documents. Maybe 20 is enough to find the gold.
And don't forget fine-tuning. If you have a few thousand examples of good hits and bad hits from your users, you can train a re-ranker for a few dollars that will beat the pants off a generic model. Google did this for every language and every country. You only have to do it for your specific business. It's the most cost-effective way to get GPT-4 level accuracy out of a much smaller, cheaper model.
It's funny, we always talk about AI replacing people, but here it's just AI helping. AI. The little AI model is the assistant to the big AI model, making sure it doesn't look stupid by talking about apple pies when it should be talking about stock options. It's a hierarchy of intelligence.
It's a collaborative ecosystem, and that's the real takeaway from Daniel's prompt. The AI revolution isn't just about the massive models that capture the headlines. It's about the entire pipeline of specialized components, many of which have been quietly evolving in the background of your Google search bar for over a decade. The re-ranker is the unsung hero of the internet.
It's a good reminder to respect the search veterans. They've already walked through the fire we're currently standing in. They dealt with the spam-pocalypse and the keyword stuffing era, and they built the tools to survive it. We're just applying those tools to a new kind of spam. The noise inside a large language model's context window.
They really have. And I think we're going to see a lot more of these old search techniques being rebranded as AI innovations over the next year. Query expansion, synonym mapping, query rewriting. Google has been doing all of this for years. Now, we just do it with an LLM and call it Agentic RAG. It's like taking a classic car, putting an electric motor in it, and calling it a revolutionary new transport platform.
Agentic RAG. Man, our industry is good at naming things. It sounds so much cooler than running a script to fix your search query. But if it works, it works.
Everything sounds cooler with agentic in front of it, but at the end of the day, it's about one thing, relevance. If the user doesn't get the right answer, the tech doesn't matter. The re-ranker is the final check on that promise.
Well, I for one am glad that the bouncer is getting an upgrade. My cat's screaming is finally going to be addressed by a truly relevant faucet fixing guide. I might even get a guide that explains how to fix the faucet using the cat, though that seems less likely.
We can only hope, Corn, we can only hope. But seriously, the next time you use Google and the first result is exactly what you needed, take a second to thank the re-ranker. It's doing a lot of heavy lifting behind that white screen.
All right, I think we thoroughly traced the family tree of the re-ranker. It started as a humble two-layer network at Google, and now it's the elite gatekeeper of our enterprise RAG pipelines. It's the intelligence in the middle that makes it all work.
It's been a journey. And it's a great reminder that if you want to see the future of AI, sometimes you just need to read a 10-year-old search engineering blog. It's all there if you know where to look.
Or just listen to us, which is much more entertaining. Thanks for the prompt, Daniel. It's always fun to look under the hood and realize the engine has some very reliable, very vintage parts in it. It's the combination of the old and the new that creates something truly special.
Vintage but powerful.
That's you, Herman. Vintage but powerful. Big thanks as always to our producer, Hilbert Flumingtop, for keeping the gears turning behind the scenes. He's the re-ranker of our podcast episodes, making sure only the good stuff gets in.
And a huge thank you to Modal for providing the GPU credits that power this show. It takes a lot of compute to keep our bouncers at the door. We're running on the same kind of power that Google used to run the whole web.
This has been my weird prompts. If you're enjoying these deep dives into the plumbing of the AI world, we'd love it if you could leave us a quick review on your favorite podcast app. It really helps other curious minds find us. Tell your friends about the two-stage retrieval and the bouncer at the door.
We'll see you in the next one.
Don't get lost in the middle. Goodbye.
Goodbye.
This episode was produced using Google Gemini 3 Flash, text-to-speech by Chatterbox.
Thanks for listening to our